Chapter 6, Lesson 2 of Pre-Calculus, and we've looked at calculating the projection vector, or the projection of one vector onto another. So, just as a review, the projection of a u vector, or a vector, onto another vector, we can calculate by multiplying the two vectors together, or the dot product, over the magnitude of the v vector, the one that's being projected onto, squared. And then we take that number, that creates a scalar number, and we multiply it by the components of the v vector, and that gives us then the components of the projection vector. So this calculation will give us the components of the projection vector. Okay, projection vector. Okay, so this calculation will give us the components of the projection vector. And very quickly, if we know that this is vector v, okay, whoops, not 4, I don't know why I wrote 4. I was thinking ahead. This is vector v, and it has, you know, two components, a, b. Okay, what did it mean? A, b. And then we have this other vector. This is vector u, and this has some different components. Let's call them just a sub 2, b sub 2. The projection of this u vector onto v is created by drawing a line perpendicular from the head of this down to the one that we're projecting onto. And then this piece that's been created from here to here, this is called the projection vector. So this is called the projection vector. Okay? And what this calculation up here will do will give me the components of this projection vector. So this equation right here, figuring out this scalar number and then multiplying it by this v vector, this will give me the components of this projection vector. Then once I have a vector, we can figure out its magnitude, because we know how to figure out the magnitude by taking then the square root of a squared plus b squared. Those would be the components of this projection vector. Okay, so that kind of summarizes what we're going to be doing. I'm going to give you a couple of examples where we do this. Okay, now if this u vector represents a force, okay, if the u vector represents a force, then the projection of u onto v, this vector here, actually then becomes how much of this force is being applied in this direction. So this vector here, u, represents a force. Then the projection of u onto v, this vector, represents then the force that is being applied in this direction, v. So if I calculated the magnitude of this projection force, or this projection vector, then the magnitude would indicate how much of this force is actually being applied in this direction. In other words, if you have a force acting in this direction, all of that force isn't being applied in this direction. Some of the force is going this way, some of the force is going this way. And what the projection vector does is tell us, well, if you're pulling in this direction at 80 pounds, how much of that 80-pound force going in this direction is actually being applied in this direction. And the projection vector will give us that. So if u represents a force, then the projection of u ends up being the amount of that force that's going to be applied then in the direction of this v vector. So let's say we have a problem where Juan is sitting on the sled, and together with the sled he weighs 140 pounds. So if I wanted to draw a vector for that, I'd draw a vector straight down, because weight, or gravity, pulls straight down. So I would have this pulling straight down. And I could calculate the components pretty easily. It's just going to be 0, negative 140. Alright? Because we start at 0, 0, our vector is pulling straight down. we then know that it's sitting on a hill at a 45-degree angle. So I can create a triangle by drawing this line here, and then I can create this other vector. Because we're going to be projecting this force onto the hill, we want this to be a vector, so we're going to make that a vector. Okay, and this is a 45-degree angle. Now we don't know what the magnitude of this is, so we can make it something simple, so we'll make it a magnitude of 1. Because if it's a magnitude of 1, then the components simply are the cosine of this angle, which would be radical 2 over 2, and then the sine of the angle, radical 2 over 2. So I have the components of my v vector, the one we're projecting onto. This force vector is the u vector, stating from our example before. So if we project u onto v, okay, so if I was to draw a line, let's see, project u onto v, remember, if u is a force, and this is a force, projection of u onto v, which would be this vector right here, if I can figure out the components of that vector, or actually the projection vector, then all I have to do is determine the magnitude of this vector, the magnitude of the projection vector, and I'll have how much force is actually keeping the sled from going down the hill. So all I need to do is to calculate the projection vector using these two vectors. Okay, so from before, we know that the projection of u onto v is equal to the two vectors multiplied together. So we're going to multiply radical 2 over 2, radical 2 over 2, the v vector, times the u vector, 0, negative 140. And we put that over the magnitude of this vector squared. Well, we made this vector a unit vector, meaning the magnitude is 1. So 1 squared is just going to be 1. So then this ends up being just that. This will give me a scalar number. And then if I multiply this scalar number then times the v vector, which is going to be radical 2 over 2 and radical 2 over 2, that will give me the components of the projection vector. Then all I need to do is to figure out the magnitude of that projection vector. So if we multiply these together, this a component times this is going to be 0. So what I end up with then is negative 140 times the square root of 2 over 2. That gives me a scalar number. So that's going to be negative 70 square root of 2. Okay? Now, if I take that and multiply it times this v vector, that will give me the components of this projection vector. All right, so that's going to give me, let's see, if I multiply this times that's going to be, whoops, I don't want to do that. Actually, I see something else. So the radical 2 times the radical 2 is going to be 2, and that's going to be those 2's reduced, which is going to give me 70 and then 70. Okay, or negative 70, negative 70. Okay, so that is the projection vector. Now, to determine then how much of this force that's pulling down, gravitational force, is being projected onto the hill and wanting it to go down the hill, I have to pull in the opposite direction in the same amount of force. All I need to do is figure out the magnitude of this vector. So the magnitude, you remember, is the square root of the 70 squared. Now, that's going to be a positive number, so I'm just going to write it as a positive number. Okay, so I can add those two together because they have the same base, so that's going to be 270 squared. And then I can, the square root of 70 squared then, because this is multiplication, is going to be 70 square root of 2. So 70 square root of 2 is going to be the magnitude of this force, and when I calculate that, that's going to give me a force of about 99 pounds. So I'm going to need to apply about 99 pounds of force in the opposite direction in order to keep Juan and the sled from going down the hill. Okay? So each of these problems are pretty much the same. You want to set up your drawing. You want to calculate the projection vector. You can make this a unit vector, and then all you have to do is find the cosine of the angle and the sine of the angle. That will be the components of the v vector. Then all you have to do is calculate the projection of u onto v. So in this example, we have a 2,000-pound car. Alright, so if we want to create our vector to do that, we have the 2,000-pound car, and the gravity will be pulling straight down, so this would be 0 and negative 2,000. Okay, and then the hill has a 12-degree slope, so different than 45. So I still want to make this a vector, okay, because we're going to project onto that vector. However, this time this is a 12-degree. Now, a 12-degree isn't a special triangle, so the components here, we need to calculate those. Now, again, if we make this a unit of 1, then the component here is simply going to be the cosine of 12, because the magnitude is 1, and remember that's simply going to be the adjacent over 1, so it's going to be cosine of 12. And then the y component will simply be the sine of 12. So this has a magnitude then of 1. So if we project then this 2,000-pound force onto this v vector, then what I want to know is what are the components then of this projection vector. Okay, so again, this is my v, my force is my u, I'm projecting u onto v, so the projection of u onto v will give me the components of this projection vector. So again, this formula, you remember, is the u vector times the v over the magnitude of the v, but the magnitude of the v in our case, because we chose to, is going to be a 1, and 1 squared is just 1. So it's simply then the magnitude of u times v, and then we're going to multiply that times the v vector, okay, cosine 12 and sine 12. So to calculate this then, we're going to multiply the u vector, which is 0 and negative 2,000. We're going to multiply that times the v vector, which is cosine 12 sine 12. Oops. And then we're going to multiply that value, and this is a scalar number. This is going to give me a single number. We're going to multiply that then times this v vector, which is cosine 12 sine 12. Okay. So basically, if I write that out a little bit, I'm going to multiply this together. So this is 0 times cosine 12, which is going to be 0. So I'm basically going to have, not basically, I am going to have negative 2,000 sine of 12. That's my scalar. And then if I multiply that times the v vector, cosine 12 sine 12, that will give me the components of my projection vector. So if I'm going to write this out, then this is going to be negative 2,000 sine 12 cosine 12. That will give me the a component of my projection vector. And then negative 2,000 sine 12 times sine 12 is going to be sine squared 12. That will give me the b component of my projection vector. So calculating that out, I have that already calculated here, I get an a component of 406.74, and I get a b component of 86.45. So these are the components of my projection vector, the projection of u onto v. Now, in order to calculate the force, I simply calculate the magnitude of this. So the magnitude of my projection vector is simply then the square root of a squared, 46.74 squared, plus the b component squared, 86.45. And if I calculate that, I get a force of about 415.82 pounds of force are needed to keep the car from rolling down the 12-degree sloped incline. Okay? So again, the projection of u onto v, if u is a force, then the projection of u onto v will give me the components of this projection vector, and then the magnitude of that vector then is the projection of how much, or is how much of this downward force is actually being deflected towards this hill. You can imagine like a drop of water. If you dropped it straight down on an incline, when it hits that, it gets deflected down the hill. Well, what's making it going down the hill is gravity is still pulling it down, but the force is being deflected, and so of the weight of that water, the weight of the car, the weight of a sled or whatever, all of that gravity is pulling down. Some of it's being deflected in this direction, causing the car or the water or the sled to want to go down that hill. And so the projection of that force onto the vector that represents a hill then would be the amount of that force that's being projected on the hill. So out of the 2,000 pounds of force that are being pulled vertically towards the center of the Earth's gravity, 415 pounds of that is being deflected down the hill.